All right, folks, we are going to get started into chapter 4, section 1. That is this for 1 polynomial functions. And we're going to start with the fundamental theorem of algebra. I'm not going to waste any time getting into this because this might take a little bit of time today. So the basic idea of the fundamental theorem of algebra, as it's written in our book, is every polynomial equation with degree greater than 0 has at least one root in a set of complex numbers. Now, to kind of unpack that statement, the first thing I want to look at is this idea of the root. When we talk about the root of a polynomial, anytime we talk about a root, we're talking about its 0 or where it's crossing the x-axis. All right, so what this is saying is if you have at least degree, anything greater than 0, so degree 1 or better, that it's going to have at least one root. And it goes one step further in implication. What this means by implication is we can say the degree of a polynomial tells us how many roots it will have or how many zeros it will have. Now, not all these zeros may be in the real number set. Notice it says complex. This is the other part of this that we want to look at. It's complex number set. All right. So when we talk about roots, we're not just talking about roots that we can see as zeros on the graph. And just to kind of go over that a little bit, if we took a degree 3 function, all right, so for example, degree 3 function, we know that y equals x cubed is a degree 3 function. So if we have y equals x cubed, we know that that looks like this, right? But there are other degree 3 functions. Now this one, if you notice, has a single root, but it is repeated 3 times, all right? What I mean by that is when you see that you have a change in concavity at your 0, that is going to be that triple root. Now, when I say that, what I'm talking about is, and we can see this right when we factor. If we factored this, so to speak, you'd say this is x times x times x. Each one of these give a 0 root, right? So when we talk about factors and we set each one equal to 0, say if we had x cubed equal to 0, let's do that instead. Let's change this and say x cubed equals 0. Well, if 0 equals x times x times x, then x equals 0, or this x equals 0, or this x equals 0. So it still has 3 roots, but they're all 0. And you can see this also in a degree 3 function that does something like this. You'll have functions that do this. Degree 3 functions will have 2 humps, so to speak, 2 rounded portions. And where we see this 0 and this 0, this one is a double 0. If, say, this was at B and this was at A, then this thing would factor as x minus A times x minus B squared. And that would be our polynomial. And this would be degree 3 because you'd end up with an x cubed, right? So this would give us that equation. Again, 3 roots because it's a degree 3 function. You could also have where we have something like this. And this is a nice one because if this is at A, B, and C, this would factor as x minus A times x minus B times x minus C. And these are all in, and again, A would be negative, so this would end up being x plus the opposite of that, or x minus the negative A. All right, but anyways, we would have, again, x cubed, 3 roots at A, B, and C. That would make this equal to 0. And finally, we could have something, and there are variations on this. I mean, they could all be turning the opposite way. By that, I mean, instead of going up here and down here, it would be the opposite. This would be up, going back down over here. There is one other way that we could do this, and that's this. Now here, we have A. So you would have a factor of x minus a. Now there is two other roots in here. They are going to be, let's say, how do I want to do this? Well, what we normally think of as a plus bi and a minus bi, right? They're going to be complex numbers. So we'd have two complex roots, one real root. Here we have three real roots. Here we have three real roots, one as a double root. Here we have three real roots. All of them, or the only one is a triple root. All right, so there's a lot of variations on this, and we have to be able to be flexible to find those roots. And that's going to be our goal in this section, is first to be able to find roots, just like we did in the last chapter, but now we're going to add the complex roots in there. And then we're going to be using roots to build equations also. So those are our two main goals. All right. So with that in mind, let's look at an example. They could ask you, state the number of complex roots of the equation, then find the roots. Well, the first thing here is I look at the degree. Degree of this function is 3. So the number of roots would be 3. All right, this is degree 3 because it's a polynomial as a function of x, and this should be equal to 0, sorry. And the equation has the highest power of the variable to be 3. So that is degree 3. That tells us by the fundamental theorem of algebra that we have 3 roots. How do we find those roots? Well, the first most obvious way is kind of like solving. We're going to factor. All right, the first thing we're going to try to do is factor this. So if we factor this, we are looking at x first. There's a common factor of x. So then that'd be x squared minus 2x minus 15. And we can also look at this and say, all right, so we've got in here, we need something that multiplies to negative 15 and adds to negative 2. So that would be, I believe, x minus 5, x plus 3. And that would tell us the roots of this are x equals 0, x equals 5, and x equals negative 3. Whatever makes each of these equal to 0. So those are roots. Now, I found those by factoring, but I could have also found those by using my graphing calculator. And I just want to be sure. I'm going to take us out of this, put us back in, make sure we have our graphing calculator handy. We could have gone in and said y equals and done this original equation. So x raised to the third power minus 2x squared minus 15x, and we could have just graphed this. Now, we can see that it has 3 roots. They appear to be at negative 3, 0, and 5. If you have any doubts, you can go to your table. And if we go to the table and go start at negative 3, what do we see here? We see the y value is 0. This is another implication of the fundamental theorem of algebra, is your roots are where, if we asked, is 0 a root? Well, if we plug in 0 and get 0 out of the function, then it's a root. All right, so those roots are where the equation value is 0. The x gives you a y of 0. So negative 3 shows 0, 0 shows 0, and if we go down, we see 5 shows 0. So that we could have found our roots right from our graphing calculator. All right, you can also, just again, to give you one that is an easier one to do, we can use that second calc button and find a 0. If it's not obvious at a nice point, say we're looking for this 0, I would go left of it, just like we did with our maximum minimums last chapter. We would go left of that, hit enter, go right of it, hit enter, and hit enter one more time, and it tells me that 0 happens at x equals negative 3. So we could do that for all of these as well. And we can use those if they come out to nice numbers. If they don't, we want to be able to find the exact value. All right, so that's where we start. All right, let's do another one. This one's going to be much more complex. And again, I want to be sure I have my calculator to work on this one. Let's see, so I do not. All right, let's do this. All right, so we've got our calculator. Now, for x to the 4th plus 5x cubed plus 9x squared plus 45x, first thing, This is degree 4, and that means it has 4 roots. Now, in this case, it could be 4 real roots. It could be 2 real roots and 2 complex roots, or 0 real roots and 4 complex roots. All right. The complex roots, the ones that involve I, will always come in pairs. That's something I should mention. So we know that if we have a set of complex roots or imaginary roots, we would have either 0, 2, or 4 of them. So it's either 0, 2, or 4 of real roots at the same time. All right, because they add up to 4 roots. All right, so I'm looking at this. First thing I know is I can factor an x out of here. So I'm going to do that first to see if it helps me with anything else. All right, so we get this. And a cubic. We're not used to factoring cubics. So what I'm going to say is, I know right now that if I was looking at my answer blank, I have the degree is 4, roots is 4, and now I've got my first root, x equals 0. All right, put it in the answer blank right away. Now I need others. There's 3 others that are in here. I'm going to use my calculator for that. So I'm going to put in just what's inside there, the x cubed plus 5x squared. So let's do x raised to the 3rd power, and then plus 5x squared plus 9x and plus 45. And if I graph that one, looks like -5 over here is a root. I don't see any others. And if we go to second table, let's see, that's just growing without bound negatively. We have the 0 we see at -5, and then that just grows without bound positively. So it looks like we've got x equals 5 by calculator, right? So we got this one by factoring, this one by calculator. You don't have to label these when you do these. I'm just labeling them so you know. We factored that. By calculator, we found this. That was a -5, sorry. And now we got to find the other 2. All right, well, let's look at what we can do. If we have no other clues to this, we could say, all right, I know that x equals -5 as a root. X equals -5 as a root means x plus 5 is a factor. So let's divide x plus 5 into x cubed plus 5x squared plus 9x plus 45 and see what's left. All right, I could do this with synthetic division or with long division. All right, in fact, let's do synthetic. We don't do enough examples of that. If I'm dividing x plus 5 into that, then that means we would use 1, 5, 9, 45, and in the box would go -5, a root. All right, so we do this, bring down the 1, multiply by -5, add, we get 0, multiply by -5, we get 0, add, we get 9, multiply by -5, we get -45, and we get 0. We should get 0. We knew that this was a root just from the graph, so we knew we should get 0. If we didn't get 0, you probably divided wrong, so go back and check. So what does that give me as a result then? When I divide x plus 5 in, I get x squared plus 9. So this is my remaining piece. So I need to know where x squared plus 9 equals 0. All right, so where does that happen? Well, let me do that down here. Be a little more organized here. All right, so we need to know where x squared plus 9 equals 0. Because right now what we know is we've got x times x plus 5 times x squared plus 9 equals 0. That's what we did by doing that division. We found the first one by factoring, we found this by looking at the graph, and we found this one by dividing in, right? Now we got to find what roots that gives us. These are the factors, right? These are factors. Factors give us roots. Wherever factors are 0, give us roots of that equation. So x squared plus 9 equals 0 means x squared equals -9. that makes x equal to, when I take the square root of both sides, the plus or minus 3i. So that would be my last two solutions. This has, and you don't have to write it as 3i and negative 3. I am doing that just so you can see there are 4 roots as we expected. And 2 of them are complex, 2 are real. And we've got our solutions. All right, again, this is going to take some practice, and I don't want to keep giving you more and more examples. We'll do more in class after the homework. I want to go to the other half of this section. The other half of this section is write the polynomial of least degree with these roots. We've done this before. We did this when we said, all right, let's look at this and say x equals negative 3 is a root. That means trying to get it set equal to 0, add 3 to each side. That means x plus 3 equals 0, so x plus 3 is a factor. Right, so we have x plus 3 as one of our factors. Remember I said anything with imaginary numbers is going to come in pairs. So this, we get x equals 2i. That means if we get x equals 2i, then x minus 2i is equal to 0, and that makes x minus 2i one of our factors. And if I got x equals negative 2i, that means x plus 2i is another factor. Right? And so x plus 2i equals 0. Now, when you have these pairs, I generally do these first because they're always going to work out the same way. These are conjugates. Notice one is it's x minus that number, x plus that number. When we do that, the middle terms go away, right? They cancel each other. If you look at these two, this is a negative 2xi, and this is a positive 2xi, the inner and outer. So all we really have to worry about is this, which is x squared, and this, which is a negative 4i squared. So what does that come out to? That comes out to x plus 4. X squared plus 4, sorry. Again, I squared is negative 1, right? This is negative 1. So negative 4 times negative 1 is a positive 4. So we would have, and let me get some here. We would have this x plus 3 times x squared plus 4 equals 0. So now we can multiply this out. We've got our factors, right? Remember, when we got roots, our first goal was factors. So now we got factors. This was the roots, just to label this. These are the roots. These are the factors. This is factored form. And now we get the actual quadratic equation. Multiply this out. We do first would be x cubed, and then plus 4x plus, and then right here would be 3x squared, and finally plus 12 equals 0. To put this in standard form, meaning decreasing variable degree, we'd have, 3x squared plus 4x plus 12 equals 0. And we have our quadratic equation of least degree that's in standard form for that set of roots. All right, similar to what we did before, just now adding in more of the imaginary stuff. All right, one last one. They gave you these, again, same directions. Write the quadratic equation of least degree in standard form for these roots, right? These are our roots. So first thing, x equals 1/2. That means 2x equals 1, which means 2x minus 1 equals 0. That is my first factor. All right, this one, 4i. If they only give you 4i, guys, you have to know that negative 4i is also in there because they always come in pairs. So I call it an implied root. It's implied then that negative 4i is also a root. If they give you one of them, the other one has to be there. And so it's kind of a tricky way of giving you that, but that's what happens sometimes in these problems. So we have x equals 4i, which gives me x minus 4i equals 0, which is my second factor, x minus 4i. And then we have negative 4i, which gives me x plus 4i equals 0, and that is my last factor for this one. And again, I start with these. When I multiply these two together, I'll still have this. When I multiply these two together, again, if you notice the pattern here, we're just doing these, so that's an x squared. When I multiply these two, this is going to be a negative 16i squared, so that's plus 16. Do you notice a pattern with that? When it was 2i and negative 2i, we got plus 4. If it's 3i and negative 3i, what do you think we're going to get? Plus 9, right? It'll be x squared plus 9. It's always going to work that way if you just have those type of roots. Now, you can still just write it out and multiply it, but there is a pattern there if you see it. So we get our factors, and these are what we're going to look for, guys. As you do these, we want to see that from your roots, you got your factors, and now we would multiply this out to get our actual quadratic. So now we have 2x times x squared gives me 2x cubed. 2x times 16 is a positive 32x. Inner would be a negative x squared, and last is minus 16. And again, when I write this in standard form with decreasing degree of the variables, we would have this. And that would be our quadratic equation. Remember, always the equals 0. It's an equation, so it has to have an equal sign. And that's it, folks. All right, we are going to be doing a decent amount of practice on this. So you need to head there and do that. And until next time, we'll do 4-2 next. Have a great day.